Assalamu alaikum wa rahmatullah. Dear students, today inshallah we're going to go through the second set of exercises for chapter 4 and chapter 5. So we will go through 5 different problems for each chapter and try to go through the ideal way of trying to solve these exercises. So to begin, we will start with chapter 4 obviously, and the first question is draw the graph of the non-return to zero invert scheme using each of the following data streams, assuming that the last signal level has been positive. From the graphs, guess the band for this scheme using the average number of changes in the signal. Compare your guess with the corresponding entry that we have studied in class. So remember, for non-return to zero invert scheme, the second bit determines whether we toggle the level or not. So if it's 0, we don't toggle. If it's 1, we toggle the level. So basically, we can try that on the pattern all zeros. So if the original level is positive, so we go for the 0, we don't change. For the 0, we don't change, and we keep doing that to the end. So that's so for 1, if the original was positive, then we go 1, so we go negative. Then if there is 1, then we go positive. Then if there is 1, we go negative. If there is 1, we go positive, and so on. So this is the non-return to zero invert. So if we are positive, then here it's positive, and then for the 1 we go negative, and then 0 we keep going, and then for 1 we go positive, and then 0 we go straight, and then for 1 we go negative, then we keep straight, and then 1 we go positive, and that's it. Okay, so for here 0, so we go positive, positive, then we go negative, and then we go positive, and then we go straight, straight, and then we go negative, we go positive. So remember, the 1 indicates that we have to toggle the level. The 0 indicates that we keep the level as is. So the second part of the question, to calculate the average number of changes. How many number of changes are here? The number of changes here is actually 0. So the average number of changes equals, we have here 0 plus how many number of changes for case B? It's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 changes. Plus, for case C, we have 1, 2, 3, 4. Okay, so it's 4. Plus, for case D, we have 1, 2, 3, 4. So again, we have 4. So the average, if we have 4 cases, the average is 8 plus 4 plus 4 divided by 4. So that's so the average number of changes is 4. The average bandwidth in that case, the bandwidth average equals to, so if we have average number of changes equals to 4 with respect to 8 bits, so we have on the average 4 changes for each 8 bits times n, it's equal to half n. Of course, this value here matches the value that we have calculated in class for C, or the average number of changes, which is half. Alright, so repeating the same exercise for differential Manchester. So remember, for differential Manchester, the way it works is that if there is a 0, then you start by toggling first, and then you toggle once more in the middle of the bit. So like this. So if it's 0, then you toggle, and then you toggle again. So each time we have to toggle once in the middle of the bit. But if it starts with 0, then you toggle at the beginning of the bit as well. If it's 1, then you keep the level straight and then you toggle in the middle. So so for 0 again, we toggle, then we toggle, then we toggle, and so on. Okay, so for case B, we start by keeping the level straight and then we toggle. And here 1, we start by straight and then we toggle. We start straight and then we toggle. Straight, 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 okay, straight, okay. Straight. Okay, so for 1 we start by toggling and then toggling again. For 1 we keep straight and then we toggle. 0 we toggle and then we toggle. 1 we keep straight and then we toggle. 0 we toggle again. We keep straight. And then we toggle, 0 we toggle, and then we toggle again. 1 we keep straight, and then we toggle. Alright, so for case D, we toggle, 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 okay, and then 1 we keep straight, and then we toggle. 1 we keep straight, and then we toggle. 0 we toggle, we toggle. 0 we toggle, 1 we keep straight and then we toggle, 1 we keep straight and we toggle. Okay, so average number of changes equals, of course in this case it's double the changes, so it's 16 changes. We have again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 16. For case B, we have 1, 2, 3, 4, 5, 6, 7, 8, so 8 changes. Plus, for case C, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have 12. And for case D, we also have 12, which makes, for these 4 cases, so we divide by 4. So this average number of changes is, so we divide by 4. So this is 4 plus 2 plus 3 plus 3. So this is 12, which means that the bandwidth is 12 over 8 bits times n. So for 8 bits, these are the number of changes, and remember here that the original bandwidth was 4 over 3 n. Not that it makes it very important, but remember here that the bandwidth is equals to C times n times 1 over r. So if the value of r here for Manchester, remember it's 1 over 2. 1 bit has 2 signal levels. So this value is 2n, which makes C here 2/3, which is also between 0 and 1. So again, the calculation here is within the range that we have calculated in class, given the fact that C is 2/3, and remember that this is calculated only based on these 4 cases. Empirically, it might be different. In the next example, we need to repeat the exercise for the 2B1Q. For the 2B1Q, each 2 bits are represented by 1 signal value, so we have 16 bits in that case. So since the 2B1Q is a little bit complicated, so I want you in that case to try to put the lookup table based on which you will map your levels so that there will be no confusion. Remember that we have the 4 different combinations are 0, 0, 0, 1, 1, 0, 1, 1. The signal level, so we can map this to positive 1 and positive 3, let's say, and then a negative 1 and negative 3. Remember, this is for positive previous level. For negative previous level, as we have done in class, we can just do the inversion. So this will be minus 1, minus 3, 1, 3. So based on that, we can say, let's say that this is positive 1 and this is positive 3. For 0, 0, we go positive 1 and then all positive. So we'll go straight all the way. With 1, 1, it was positive. Then with 1, 1, we go negative to minus 3. So this is minus 3. Then 1, 1, and it's negative. So we go positive plus 3. Then it's positive, then we go negative. Minus 3 plus 3, minus 3 plus 3, and so on. Okay, so for case C, it was positive, so 0, 1, positive 3, so we go positive 3. Then it's again positive, so we go positive 3. So this is 3 and this is positive 3. So for 0, 1, 0, 1 all the way, so we go straight positive 3. So for 0, 0, 1, 1. So at the beginning, for 0, 0, it's positive 1, so we go like this, and then 1, 1. 1, 1, we go to minus 3. And then for 0, 0, for 0, 0 for negative, so we go minus 1. So 0, 0, and the previous level is negative, so we go minus 1. And then 1, 1, and the previous level is negative, so we go 3. And then 0, 0, positive, so we go positive 1. Then 1, 1, and positive, so we go minus 3. Then 0, 0, and it's negative, so we go minus 1. Then 1, 1, and it's negative, so we go plus 3. Okay, so that's a little bit tricky. So again, we'll calculate the average number of changes equals to, here, no changes, so for case A, so it's 0, plus for case B, it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 8, plus for case C, it's 0, of course, so it's 0, plus for case D, 1, 2, 3, 4, 5, 6, 7, so it's 7. So this is divided by 4. So this is equal to 3.75, and then the bandwidth equals to 3.75 over 16 times n. And if we calculate this, remember that it's this is equal to C times n times 1 over r, where r here is 2. So this makes C equals to 3.7 over 8, which is again in the range between 0 and 1. Okay, so next exercise, what is the result of scrambling the sequence 1, 1, 1 in all zeros using one of the following scrambling techniques? Assume that the last non-zero signal level has been positive. So this is very important, especially for scrambling techniques, as we have discussed in class. So remember, for B8ZS, we substitute each 8 0 bits with the pattern 0, 0, 0, then violet B, 0, violet B. This is for, of course, AMI, so the alternate mask inversion. So for AMI, the 0 is represented as 0 voltage, and the 1, for the 1 we toggle previous level. So for 1, we started with positive, so we go negative. Then 1 we go positive, then 1 we go negative. So now we can map the 8 zeros to 0, 0, 0, then violet. The violet here will have to map similar to this, so it goes negative, and then bipolar, so it goes like this, and then 0, and then violet, so we go positive, and then bi, we go negative, and then we go straight. The remaining part is 0, 0, 0. For HDB3, we have two cases. We have for even number of previous ones, then we go B00V. If it's odd, then we go for odd number of ones, then we go 000V. And we map each 4 bits. Okay, so based on that, we will go again. If it's 1, then we go, and it was positive, then we go negative. Then it's 1, we go positive. Then it's 1, we go negative. Then we have 4 consecutive zeros. So for these 4 consecutive zeros, the number of previous ones are odd. Then we go 0, 0, 0, and then V. So this is V, and this is 0, 0, 0. Then we have another 4 consecutive zeros, and the number of ones in the middle, remember the number of ones is 0, which is even. So in that case we go bipolar, and then we go 0, 0, and then violet, and then that's it. Then we continue 0, 0, 0, because the number of zeros here is not 4. So this is B 0, 0, violet. Next exercise. So for next exercise, we have a baseband channel with 1 mega. So bandwidth equals 1 megahertz. What is the data rate for this channel if we use each of the following line coding schemes? So assume that the case factor is 0.5 except for MLT, so use a case factor of 1/3. Okay, so this to match the value of C in the table, and remember we talked about that in class, that the case factor for the case of MLT is less than half by design. So for case A, we know that the bandwidth equals to C times N times 1/R. So this is valid for all cases, of course. So the bandwidth, which is 1 megahertz, equals to case factor, which is half, times N times, for non-return to 0, remember R is 1, which is the number of bits divided by the number of signal elements is 1. So this leads to the fact that N will be 2 megabits per second. So for the case B, which is for Manchester, For Manchester, remember, the R value is number of bit elements divided by the number of signal elements, so that's 1 over 2, which leads to the fact that the bandwidth equals half times n times 1 over 2, which makes n equals 4 times the bandwidth, which is 4 megabits per second. For the case C, R is equal to 1, of course. For the case of MLT3, the R is still 1, and C is 1 over 3, so the bandwidth equals to 1 over 3 times n times 1 over R is 1, which makes the bit rate equals 3b, that's 3 megabits per second. For the case D, the 2b1q R is equal to the number of bit elements divided by the number of signal elements, so which leads to the fact that B equals to half times n times 1 over 2, so that makes n equals 4 megabits per second. Okay, so that's for these are 5 exercises for this chapter.